Welcome to today's Research Pays Off. I will just briefly introduce our speaker and then let him take over. So Dr. Bernard Izevbekhai is the research operations engineer covering concrete research, geotechnical research, and analysis of pavements related issues at the MnDOT Office of Materials and Road Research. He holds a bachelor's degree and a master's degree in civil and structural engineering from the University of, I should have read through this and asked you for pronunciation, Bernard, Benin, Nigeria. Hopefully that was close. And a Master of Science in Infrastructure Systems Engineering and a Doctor of Philosophy in Civil Engineering from the University of Minnesota. He received honorable mention in the Centennial Book of the Transportation Research Board of the National Academies in 2020. He was also part of the research team that innovated the quietest concrete surface in the world, which was from 2007 to 2010. He invented the aggregate avoidance index method for evaluating the interfacial strength of pavement materials in 2014. His expertise includes mathematical modeling, infrastructure systems evaluation, stochastic analysis, and dynamic systems. Thank you to Bernard for offering to present today, and I will let him take it over.
All right. Thank you, Lauren, and thanks everybody for showing up on this very wintry morning. Well, wintry morning because I'm in Minnesota. I know it's 90 degrees in some parts of the country, but thanks for attending this presentation. So today we'll be talking about IRI-induced excess fuel consumption and specific to heavy-duty truck traffic. And the first thing I would like to do is to acknowledge my co-author, Mr. Glenn Engstrom, who was the Office Director for the Office of Materials and Road Research, MnDOT Office of Materials and Road Research, retired recently, and currently he's the Director of Engineering at the Aggregate Ready Mix Association of Minnesota. And to thank Jeff Bronner, our research director, who is always very supportive of good research. And he is a very, very encouraging force when it comes to the research that we do. And Kurt Turgeon, our pavement manager, and then Melissa Cole, our pavement management engineer, and Steve Henricks, our assistant MnDOT, the MnDOT Assistant Pavement Management Engineer. He was in pavement design as at the time he helped extensively with this study. And Annika Christensen, she's now a Ph.D. student at Oregon State University. She was one of the student worker paraprofessionals who helped us over the past couple years with some of our research. We'd like to create some form of a, let me say, a skeleton of what we'll talk about. I don't stick very rigidly to this, but why are we even talking about LCCA? I mean, why are we even talking about fuel consumption? And then why are we doing this presentation at all? Why did we do a study? I just wanted to mention that this study and a paper that came from this study has been accepted for publication and presentation at the Transportation Research Board Conference of the National Academies. And Glenn and I are the authors of the paper. So why did we bother, the midnight oil and all that to do this analysis? So, and we will just also talk about previous studies, what led to this, what led to our method, because there's a method to our, I would say, our sanity or our wisdom in approaching fuel consumption, excess fuel consumption in this manner. One of the comments we had from TRB was that this approach is a novel approach, and nobody has ever really used the performance curves for the various interventions to do this study. So it's the uniqueness that was very interesting to the national academies. And then the whole process of choosing a model. What's the workable model? There are many models out there. A lot of people have come up with models for VOCs, which is vehicle operating costs, and part of which is fuel consumption. There are a lot of models that are try to transcribe pavement pavement vehicle interaction into fuel consumption. There are many of them out there, but how did we choose the one we chose to use? And finally, how did we get to do or create the indices that we are the indices that we are presenting today, and so on and so forth, and then some kind of a recommendation at the end. Okay. So I did talk about many models out there. We decided to use a World Bank model called the HDM-4 model, and we'll explain why as we go further. And another thing we did was to work on the sigmoidal curves. We have sigmoidal curves of IRI versus time for the various fixes that our pavement management has in the pavement management system. I believe most states have something similar, because definitely over the years, you may have developed some default curves for the various interventions. And if you don't, you probably have the data, you just haven't developed them. But they are there and they speak volumes, because when push comes to shove, if you want to rely on just sending out a vehicle there to measure fuel consumption, that method is fraught with a lot of variables, because temperature, pressure, road condition, and a lot of other things would even add or subtract from your actual fuel consumption. But if you want to do an analysis of the IRI induced, that's the roughness, pavement roughness induced fuel consumption, and there is a performance curve for a particular intervention, then that performance curve has already taken a lot of things into cognizance, and it can be used as a comparative method, not necessarily as, it can be used comparatively, because over the years, these performance curves have been developed. And again, we are not here to reinvent the wheel. A lot of work has been done. A lot of people developed the HDM-4 model, and a lot of people have transcribed it into fuel consumption in various ways, but nobody has actually used the performance curves, and that's where we come in. Over here, we'll be mentioning ride quality index. What's ride quality index? This is what MnDOT uses in her pavement management system. It is a rating that's ranging from 0 to 5, where 0 is extremely horrible, and then 5 is very good. When a pavement is new and pristine, what we expect is that when people ride on it, they'll have a rating that's about 5. That's what we always hope for. That might be utopian, but to a very large extent, that's the hope. Some do make very close to it. These days, in those days when people will grind, they will grind to about 70 inches per mile. But these days, people grind to about 30 inches per mile. So technology is improving. So you will find that people are really hitting that 5 very well these days in terms of the ride quality index. How do we do it? We blindfold. Well, we don't really blindfold people. We make people take individuals and make them ride on a particular section and score it. And some of them are wise enough to close their eyes so that they're not influenced by other things. Oh, the scenery is so bad, it's so beautiful, therefore it rides well. No. So, and with that rating, we use a vehicle. Excuse me. We bring a ride measuring equipment to like a high-speed profiler or the pavement management van, and then they measure behind, and they have the International Roughness Index, which is a quantitative measure. And by the correlation of International Roughness Index and RQI, then we have but then we are able to, because we cannot carry people and do the rating all the time. So we're able to have RQI in our database because we measure IROI very many times during the year and develop and use its correlation curves to now record RQI. And then I'm now left with the need to define IROI. But before then, everything we're going to talk about here, the service life, in our service life evaluation, when we talk about the service lives of our pavement, we say that when the ride quality index is 2.5, that the remaining service life is 0. So we measure our service life up to a point where RQI is 2.5. So essentially that's about 2.1 or 2.2 meter per kilometer IROI, but IROI goes up. The worse the pavement is, RQI goes down, the worse the pavement is. So they cross. So the correlation curve is a kind of negative indicial function that correlates IROI to RQI. Now, IROI is the generally accepted or international roughness index, which shows that it's international in nature. It was sponsored by the World Bank in the early 90s by, the World Bank, and they actually did some runs in Brazil in order to develop that index. And what is right actually? What is roughness? A pavement has features that would introduce some dynamics when you ride. That will make you feel comfortable or uncomfortable when you ride on it. Now, how do we quantify this? If you have a system that has peaks that correspond to the resonant frequency of the body, then as much as possible, we simulate what is comfortable versus what is not comfortable. And that's what IROI kind of measures. IROI has 2 peaks, and we'll get to that. So IROI is a general pavement roughness indicator. It estimates the relative movement of a vehicle, but that's not all, the vertical movement of the vehicle. But it uses the vertical acceleration to compute it feeds the quarter car with the summation or the various vertical accelerations, so that the quarter car uses those factors, those constants that I show on the right-hand side, uses those constants to now generate something that is indicative of how rough the pavement is. So a good riding pavement, a newly diamond ground pavement in modern day, might be 30 inches per mile, 35 inches per mile. And when you start to get to about 120, 130, then you begin to think of what next to do. Probably some minor rehab, as the case may be. So that will give you IROI. Now, if you have 500 inches per mile, I can assure you that you cannot ride on it, because you're very, by the time, the internal organs are beginning to respond to the dynamics, then that's very uncomfortable. And so one of the greatest measures of how we feel, of how good a pavement is how it rides. So we work assiduously to ensure that our pavements ride well. But it turns out to be that the worse riding it is, the more fuel you have to consume. And that's another reason why, a sustainable initiative would include ensuring that the pavements ride very smoothly. And by riding very smoothly, it means you reduce the international roughness index tremendously. Mathematically, Sayers in 1995 gave a definition of international roughness index. And you can see that integral there. It actually shows you that the slope power spectrum density as a measure of another definition, alternate definition of IROI, the average rectified value of the slope power spectrum density is a definition, a secondary definition of IROI. So that's what that equation is actually doing, the equation by Sayers. And I do show two peaks there for the gain algorithm. And many times I told people who wanted to use rod and level to measure IRI. I said, well, your rod and level or whatever you have, your survey equipment will measure a profile to give you a profile. But that profile is not your international roughness index. It's not your roughness profile. That profile is something that the quarter car will have to reinterpret because the various waveforms that are encasted, I would say, within the within your profile are what the quarter car algorithm is going to pick up. The quarter car algorithm has a multiplier or a gain function that amplifies certain frequencies to the point that you have, first of all, body bounce and axle hop. These are the two peaks that you see in that gain algorithm. So you see that the IRI measurement, what the quarter car tries to simulate is really how you feel, based on certain waveforms. So it's not really just the profile itself, but what the quarter car interprets that profile to be in terms of how comfortable you will be riding on that surface. So concerning the fuel consumption that's based on IRI, MnDOT has had a lot of studies. In 2011, we brought to the United States Technical University of Gdansk, Poland, within a certain extension of a pooled fund. And they came in 2021 and in 2011 and 2014. And one of the things we found out was they did a distribution to see how rolling resistance, by the way, talking a little bit about the kind of rolling resistance they measured, they canceled out IROI because IROI in itself will work within rolling resistance and will work under powertrain as well in terms of the resistance that the vehicle undergoes, while it's operating on the roadway. So people, the Mark 4 actually did cancel out IROI so that we were left with rolling resistance. Now, the rolling resistance is a measure of the kind of resistance the vehicle encounters while moving, and that resistance is not due to hydrodynamics, neither is it due to friction, but it's a resistance that the surface imparts on this. So because of the confusion and the fact that there's a lot of intersection of rolling resistance and IROI and then friction, and people are not able to really separate one from the other, the feds now came up with PVI. So when they're analyzing all these things that have to do with rolling resistance, effect of IROI, effect of deflection, and so on, they will just say PVI, which is pavement vehicle interaction. It helped to make these things less cumbersome, right? So you can see that distribution that for rolling resistance, the means of a rigid pavement and an asphalt pavement or a flexible pavement are pretty close. They're pretty almost coincident. However, the left tail, in the PCC tends to be more towards zero than that of the HMA, and the right tail of the HMA tends more towards infinity, but slightly more than the concrete. So within that enclave, within that large intersection, which is about 80% almost of the total of the two distributions, the overlap of about 80%, a lot can be done in making the pavement to ride smoother. And then you would see that with smooth riding pavement and even high rolling resistance, you can have low fuel consumption. So when we saw these, we took we retained a company called Fuel Miner, and they went to two very bad. We made them go to two very very poor riding sections. Highway 66 is an asphalt, and Highway 10 in Satel is a concrete pavement. But what they found out actually showed that there were some features of the which they had already originally interpreted as rolling resistance. There were some features in the concrete that were occurring at a certain frequency, and with that frequency, they could pick up the fact that there was a real pull, some energy loss on the in that concrete, and that was coming from the joints, because the joints were actually short due to the age of the pavement and the way it was. There was a lot of faulting, but it showed up probably as poor IROI, and they did notice that that was actually contributing tremendously to the power loss in the vehicles. They made the same observation at Main Road. They made the same observation at Main Road. There's a 2.9 Hz concrete power loss. So you can see that those are the features that trigger IROI: faulting, warp and coil, all manner of distress types. Those are the things that trigger IROI. But even though when looking at the effect of IROI on fuel consumption, fuel miner picked up the IROI implicating features of certain pavements and projected them to be causative to the calculated fuel consumption in those test cells, and as well as the network test cells that we looked at. So when we brought Technical University from Gdansk, Poland, we actually, that's the Mark IV, which is the #1 rolling resistance measuring equipment in the world. So we brought them here, and the principle by which it works, you saw some 0.003. It's a torque, divided, if for a, I just want to go back to the fundamentals of mechanics. I don't need to. Well, when you have your moment of inertia and you have angular acceleration, what the Mark IV actually does is, at the end, it converts that angular acceleration into a torque, the angular acceleration into just a rotation in radians. So when you see rolling resistance measurement coming from, say, what's this? Just have 0.003. What does that mean? It's just a torque, and it's the angular acceleration, the angular displacement that is due to a torque. That's what the Mark IV normalizes. So, but they had to cancel out IROI so that they could get just the effect of rolling resistance in this device. But it told us a lot, like the kind of fuel consumption numbers. There are a lot of variabilities when it comes to the influence of like 10% saving on rolling resistance will result in 2 to 3% reduction in fuel consumption. There are a lot of variables that can influence that, but these are some of the findings which we made when the Technical University of Gdansk came and did their measurements at Main Road. They came in 2011 and then 2014. And also, if you look at this distribution, like this is the distribution we got from those two very horrible pavements, that there is a lot that can be done in the section that has to do with engine thermal. Those more or less unknown. It's all not just engine thermal. It's working against certain things. It's working against certain, features, certain distress features. It's working against things like faulting, rotting, as the case may be. And so it's within that enclave that we believe very strongly that the fuel consumption belongs. I have talked about these are various normal distributions that we came up with. You see rolling resistance of 0.007 something and 0.007 something for concrete and asphalt. They are pretty close from what we observed at Mean Road. Mean Road presents test cells that are we measure in real life, real time, so you can normalize. You can be sure that you haven't gone into a difference of temperature and so on within a day, a measurement that's done in a couple hours, or significant temperature changes. So here we have a situation. Again, this points us to the fact that there's a lot that can be done. That if the pavement rides well, if it rides well, you are likely to have improved fuel efficiency. Okay, so I created that little envelope to show the area where I believe the fuel consumption belongs. Okay, and I'm going to show something here. I'm using a method, a very not too common didactic method, and I'm going to give you this result. And then from this result, I will now go back and tell you how we arrived here. I'm watching my time now. Okay, the very first column there shows the intervention. There you see bituminous construction, BAB construction, that's bituminous rural construction, urban construction, and so on and so forth. And of course, the next slide shows some more of these, more of the concrete in the next slide. The second column shows the current proposed. And what does those mean? In 2018, we had the network, the data in the network as at that time, I called them current. In that same 2018, we reevaluated, based on things that had been added since the performance scores were developed many, many years ago. And we found out that we could propose certain things because some changes had occurred. So you see on the third column where it says HPMA life, that's telling us here that the current is 16 for the very first one. And then 16 was what was proposed. So not much changes had occurred there, okay, for the BAB, okay. Now, these are based on 2018. Now, a recent one has been done in 2022, 2021, 2022. Those are not here because there's still a work in progress. So this is based on 2018 and pre-2018. Okay, so the weighable life, I will talk a little bit on why should we even have a weighable? The HPMA life was from core fitting. Now, weighable method is a very powerful method, and we calculated the weighable life, and that's what you see there. Coincidentally, in that very first line, the BAB rural construction, you had 16, okay, as a service life. That's the expected service life based on Weibull, and it's not always the same because Weibull approaches things differently. Weibull doesn't use normal distribution. It does the analysis and it tells you what distribution your data is. So it's a very powerful method. What is the annualized mean? So what we did, we transcribed the HPMA performance curve. We transcribed it into IROI, and then we now came back. After transcribing to IROI, we multiplied with the HDM-4 transform model, and we came up with an index. Then we annualized it, divided by the number of years, and just had, so it would be like the bars. If the bars were all the same, if your IROI wasn't changing at all over the years, the height of the bar would be 1.42, just something like that, okay? And then for 70 kilometers an hour. So the first set there, 70 kilometers per hour, the next three for 100 kilometers per hour. That's the way the HDM-4 presents it. So we decided to just use the HDM-4 and not introduce other factors or other variables. So the NPV, in the NPV, we had that transform, but we normalized it. We used the net present value, like a net present value computation. And what that does is that just like when you're doing NPV, you do an investment in a particular year, and then you bring everything to the first year. It's a way of compensating for those pavements that last very long. And because they last very long, they have a very lengthy period in which to consume fuel. But we're trying to provide a kind of benefit for being above 2.5 for very long and consuming pavement relatively less because the IROI is good. So we had to normalize using the net present worth, and then the using net present worth, and then we did a normalization of the net present worth. In which case, again, we divided by the service life in order to normalize it. So these are three very independent indices. Now the same things in column 5, 6, and 7 are replicated in 8, 9, and 10, but for a different for 100 kilometers per hour. Now these are the numbers we arrived at. Well, not only did we do this, we went further and we said, let us look at what happens every 50 years. If I build an unbonded overlay, it lasts me 35 years. I'm going to come back and do, after the unbonded overlay, a minor rehab, which is about 15 years, plus another, plus a little bit of a major rehab, or just a minor rehab. So we're cascading the things that happen after a particular intervention. So we approached our pavement design and asked them, what do you do after a concrete, an unbonded overlay? What do you do after a BAB, and so on? So we got the precedents, not really using the years they recommended, but we're saying if everything goes well, on a particular, based on this service life, then those are the things that will be done after those service lives. So we took these values for each of those interventions and we did a summation up to 50 years. And at the end of that summation, we divided by new concrete construction to get these ratios. So these are ratios that we got based on the new concrete construction. So a few more here, and you can see that for the major concrete construction, CD, urban construction, that we have a 1, 1, 1, 1, 1 because everything was normalized to this. Okay. All right. If it's less than 1 here, it means that you have a system that's consuming less fuel. If it's more than 1, it means that it's a performance curve that is consuming more fuel. So that's what we have. Now, the difference between this and another state or another entity, they might have a different set of precedents or a different set of succeeding interventions to each of these interventions. And your service lives might be different. So, but this method will work anyway. And we are guaranteed that it will work, even though we are still recommending at the end of the day that the consultant should show us how best to use these factors in our life cycle cost analysis during pavement selection. So how did we get here? I'm now going to go into how we got to those results. So like we said, we validated the remaining service lives, and then we applied the HDM-4 model. Then we did various summations to develop 3 indices after a cascade for a 50-year period. And then of course, that was based on referencing everything to new concrete construction so that you can easily see it at a glance. Anything that's more than 1, has lesser fuel consumption. If it's less than 1, has a lesser fuel consumption than CD new construction. And if it's greater than 1, it has more, just to create a perspective. So we can also do the ratio with BAB. And so we can easily see anything that has less than 1, has more fuel, less fuel consumption than a BAB. So That's a bituminous on aggregate base. That's a brand new construction of bituminous. So there were some governing equations, but I'm sorry, this is the best I could for the HDM-4 model. Like I said, we're not reinventing the wheel. We looked at the various models critically, and by we, I'm talking about Glenn Engstrom and I, to see why we shouldn't use the UIU University of Illinois Urbana-Champaign, that is UIUC method, or why we shouldn't use the European method, the Miriam method, or why should we use the HDM format? We went into a lot of studies to see that to arrive at the fact that the HDM-4 model was actually robust, and it had been developed over time, and it has stood the test of time. So we chose from all these the HDM-4 model, and that's essentially what the HDM-4 model provides in terms of a relationship with IRI. Okay. Now back to our sigmoidal model that gives us the IROI performance over time in our network. This is how the IROI and RQI, these are the transforms. The transforms are different with various pavement types. It's different, for flexible pavement and for rigid pavement. So with this, we transcribe first and foremost our data from the pavement management system, which we got from the pavement management system. We converted them into IROI because the HDM-4 is a correlation between IROI, not RQI, and fuel consumption. And this is our sigmoidal model. This is what it looks like. I will go back to that slide, but let me just talk about this. The beauty of a sigmoidal model is that it has to mimic this. Sorry. Lauren, was there a question or something?
I think someone got unmuted somehow.
Oh, okay. All right. So the beauty of a sigmoidal model, and I'm glad that MnDOT has a sigmoidal model, is that it has to mimic the way pavements behave when they are failing or when they are approaching terminal serviceability. There is a zone, the horizontal zone, near horizontal zone, where you can do your preventive maintenance. Because if you do preventive maintenance when your pavement is already going into disarray, it doesn't make sense. It's not preventive at that time. That provides you the preventive maintenance zone, the horizontal part of that performance curve. And then when you're approaching a point where you begin to have a value, your dy over dx is not 0, but it begins to adopt a value that is significant. So at that time, you cannot really do preventive maintenance anymore. Okay, and you get to a point of inflection. At the point of inflection, that's a little bit higher than the actual point of inflection. It should be somewhere lower there, where your second derivative is actually close to 0. At that point, you begin to think of more significant repairs occurring in your system, if that's the time you are intervening. And then you get, after the inflection point, then you get back to a point where your derivative starts to adopt a value, and a value that ordinarily would have, but we just use the reason why we're using absolute value is that the IROI curve will be different from this. It will be opposite, to be a mirror image of this, so it will be increasing and not decreasing. Okay, and then this thing starts to tail off, and there you have your dy over dx approaching 0 again. The sigmoidal curve, it looked very complex, but it's a sigmoidal curve you need to mimic such a thing. And that's why if you just use a decay model, the one that just keeps going down, you might not really get those features over time. So that's the reason why we salute the sigmoidal model. And if MnDOT is going to have a change in this sigmoidal model over time, because we are seeing something that fits the curve better, it will still be a sigmoidal model. It might not have all the features that this has, but it will have the log 1 over h or a log of 1 minus something. or or an exponential function somewhere, or a denominator that's an exponential function, so that you have the sigmoidal curve. So essentially, the MnDOT has a sigmoidal curve where these constants are different for the various interventions, and it's been able to, when we made a proposed remaining service life, what we did was that we changed. We were able to do curve fitting, and we did reduction of the squared residuals to 0 in order to arrive at the new values at which this function is satisfied, and that's why we were able to propose for the new. So sorry, that's how we were able to have the proposed instead of the new. For the current at that time, we just used what was there, but for the proposed, we went and changed these based on the way the pavements were now performing. Okay. And then the weighable numbers. Why did we use the weighable value? I go around telling people that Weibull, he was a civil engineer. You know, he's a Swedish mathematician. Actually, he was an engineer. He was a civil engineer. He developed this because he wanted to be able to evaluate the performance of infrastructure. But who stole it from him? It's all these Six Sigma people who do manufacturing. They stole it from him because they found the method to be very powerful. So they stole it from him. And when later the military saw that this was a very good thing, so the military people took it and tried to bring it back to infrastructure. So everybody has tried Weibull. Nobody has dropped it. And I don't see any reason why it should be any less with us who are doing infrastructure. And I challenge every state of the union. After the freeways were built, we have enough time for most of our interventions to have reached a stage where we can actually define their performance curves. And the Weibull method is the best method to do that. The good thing about the Weibull method is that it doesn't tell you what it doesn't say, okay, first make it a normal distribution and then we will solve it. No, like other things when you are doing some statistical tests, say, well, assume a normal distribution. Weibull doesn't tell you to assume anything. It solves the problem. It gives you the location parameter, which is your preventive maintenance window, very important. It gives you a window where you can do very little things to extend life. And then the scale parameter is the service life where we're talking about. So the service life, the characteristic life, gives you the characteristic life, which is the 63.2 or 0.2 percentile value of your service lives. Based on that would be not the Ph.D, but the CS, the cumulative CDF, sorry, instead of the PDF, the cumulative distribution function, cumulative density function, I beg your pardon. So it will be the 63.2 percentile value of the cumulative density function. And then your shape parameter, it just tells you whether your system is failing quickly. If it's infantile, then it's failing early. Or if it's end of life failure, that's not too bad, because when you design a good system, you want it to fail with end of life. But if it's failing randomly, that's random failure mode in Weibull analysis is the same as uniform mode of failure. Strange, but true. So the Weibull method is good. That's the best way to find service lives of your systems. You can use it in anything. The Six Sigma people, they use it. We don't care about Six Sigma. We do like 2 Sigma, 1 Sigma in infrastructure. We're okay with that. So it's a very powerful method. That's why we just put it there. Also, you have the service lives that we got from the Weibull analysis. And the arithmetic for Weibull analysis is so simple. You can do it straight from your Excel spreadsheet or from any spreadsheet or any kind of analytical software, or you can just do it by yourself, without even invoking any form of software or anything. So it's such a such an easy process, and I've put the equation for the characteristic life there. 2 ways of determining the Weibull gives you 2 ways of determining the service life. So just to give an example of how we did the sigmoidal function, that's a current and the proposed based on curve fitting. I believe this may have been unbonded overlay. So we did that, and then we proposed what was proposed. We wanted to give to the pavement management unit, but they're actually doing it this time around so that they have things that are more current than 2018. Okay, how about IROI? Why are we even concerned about IROI? The quarter car has the features that I gave the arithmetic values of the dashboard constant, the spring constant for the unsprung mass and the sprung mass. And it's the vibration dynamics of the quarter car that later gives you your IROI. So it's mimicked by the quarter car. So if you see, if that pavement is rougher, of course it will have more influence on the unsprung mass, on the unsprung spring, on the spring of the unsprung mass, and then the spring of the sprung mass. And at the end of the day, it will give you a different value. So what's happening below there in that figure is what is influencing what the quarter car will finally spit out. So the roughness of your pavement is actually truly measured by the International Roughness Index. Now, there are a lot of complex equations out there, including the HDM-4 equation that really does a lot of things, with fuel consumption and all that. But remember, the work that was done by Lularam, Mehdi Akbarian, and Franz Joseph that developed that curve that we had shown at the beginning that had IROI on the y-axis, fuel consumption on the y-axis, and IROI on the left axis, derives from this equation we are seeing here. But I still felt to put it here because this is going to be available. I believe this the YouTube would be available, and this presentation will be available to all who seek it. Now I'm going to run through these are the equations we use. We developed these equations in order to be able to convert and these equations are actually represented by that curve for 70 miles an hour, for 70 kilometers an hour and 100 kilometers an hour. You know how significant those are in our network. So for the cascading, we obtained the precedence from our pavement design engineer. So it shows you here that what it follows after a BAB, and it shows you what follows after a CD construction and so on, what follows after that and after that and after that. So we're able to we use the service lives that we already had, and then we now still show these precedents after that. So in your state, you have your precedents, you have your interventional sequence, which might be different from this. It doesn't.
Bernard,
yes.
I wanted to just let you know that we have 10 minutes left.
Okay.
I don't see any questions in the chat so far, but just wanted to be sure we leave time for that. Thanks.
All right. Okay. I'm almost done. So, so essentially, it's with this approach that I've already talked about that we came to for the individual fixes. These are the values we got for the individual fixes before the cascading. Still individual fixes. And then we did the cascading, where we now arranged all the fixes in the sequences in which they occur. And for each initial fix, we now recorded the value. On cascaded, we hadn't yet cascaded. So these are the individual values. So if someone's trying to look at the various individual values, they are available here. These are what we got before we now cascaded. That is, we now did the various sequence of fixes for each of the fix that is showed on the left, in the left column. And finally, we divided by corresponding values we had for new concrete construction. And at the end of that, we have these simple ratios that actually show you how the various fixes compare with the various new concrete construction, and for each of the sequences that are occurring with each of them. So these are based on not just the individual fixes there, but the sequences that occur immediately after them. So essentially, that's the table we had. But in conclusion, I want to say that IRI-induced excess fuel consumption, you notice that it's higher at 70 miles per hour than at 170 kilometers an hour than 100 kilometers an hour. It's true because of the mechanism with which not just a quarter car, because vehicles generally operate. You start to consume fuel less, because you are moving at a higher speed. Your relative consumption is less, but you will say that the dynamics increase with higher speed. Yeah, that may be true, but the quarter car model, the HDM-4 model projects that there will be lesser consumption at 100 kilometers an hour than 70 kilometers per hour. Think of when you're changing gear to a higher gear, and so how easily it is to move the vehicle. Initial values are reduced. Aerodynamics do play a part, but we try to isolate this from these analysis. Rolling resistance across the board and the corresponding fuel consumptions are pretty close, I would say. I know a lot of people like the MIT has done some studies, but what we have is what we know, it's what we did. We brought the Mark IV from Technical University of Gdansk, Poland, and the values we got that show the close proximity and an ability to do a lot by making your pavements to be smoother. You can help your fuel consumption a great deal. Now, still something that people are wondering, why haven't I mentioned it up to now? Excuse me, sorry. Okay, there's something wrong there. Okay. This is the flow chart for our pavement selection. This is not the one that the district does. This is the one that will tell you whether the district will do it. But it flows starting with the size of the project, starting with the expected design life and all that. There's a flow chart that is followed. And then an LCCA is done. Life cycle cost analysis is done. While doing this life cycle cost analysis, if we have certain indices, very powerful indices like what we found out, they can be used in a rational way as multipliers for the life cycle cost analysis. The main reason we did is there was a legislative move that actually required us to do this calculation. Although they haven't formalized it, they haven't, made it a law that this calculation is going to be done and is going to be required, so that a factor that's based on fuel consumption of pavement types will come into the process of LCCA. Although it doesn't happen, it can happen at any time. But we have preemptively done this, and who knows, it might happen in another state before it happens in Minnesota. But Glenn and I, with Glenn's leadership, we decided to do this anyway, ahead of time, so that somebody can come later and apply these indices, either geometrically, arithmetically, or exponentially in the life cycle cost analysis process. Well, with that, I want to thank you for your attention. This is not a very simple topic. It's not very simple to convey, but your attention has been very beneficial, and I thank you very much.
Thank you, Bernard. I don't see any comments or anything in the chat, but if anyone has any other questions or comments, you can feel free to unmute yourselves and just speak directly with Bernard. I'm seeing some applause reactions.
Bernard, quick question.
Yes.
Great presentation. So how do you account for the foundation in your analysis? do you, like for example, the example of trunk highway time versus 60, I forgot 62. Do you account for the foundation condition, like the subgrade or any?
Yeah. That's Dr. Raul Velasquez, and he handles geotechnical research, and he's been, let me say, the best hire that I've ever done in my life. So, so Raul, thanks for that very intelligent question. You see, what we did in this study was to look at the relative fuel consumption indices. We tried our best to do that because the things that will influence fuel consumption, you know that. For instance, if your vehicle is due for servicing, it's consuming more fuel, isn't it? And then if, for instance, it's a very windy day, aerodynamics coming. Oh, if it's like a typical Minnesota winter, your heater is on, you're consuming more fuel. So there are very many factors across the board. And truly, foundation factors do contribute immensely to IROI. So that's why we felt it was best to just capture the IROI trends for the various fixes. Because if you had heave, of course, if there is a pavement type that is susceptible to heave, maybe who knows, a particular, and that's why our pavement management system tries to do a separation of BAB from BOC and so on, because things are happening below, and at the same time you have BAB is on aggregate base. So the foundation condition plays a part. If it's on, like we did a study where we looked at drainable bases, and we were able to isolate from the network the various drainable bases, the OGAP, the DSB, the GJD, and all the various, and of course, you know very well about that. And we did see that there were influences, but so far those influences couldn't really pick it up network wide. But on a project level, we will pick them up. Yes, for sure, we will pick them up on a project level. So those things come into play and they would have influenced IROI. And I want to tell you something we observed in 2012 when we had that multiple cracking on cell 6. Was that cell 6 again? We had the multiple cracking. Yes, I believe it was cell 6. We had used a special OGAB. It was when we were doing the forensics, we now went back because the OGAB was failing. It was fragmenting. It was changing its consistency. So as it was fragmenting, there was subsidence. And that subsidence, when we were now doing the forensics, we went back and said, why don't we just check the IROI? And we checked the IROI. We found that at a particular point, the IROI had begun to spike. So the foundations influence IROI, whether we know it or not, whether we like it or not. So, but this analysis method try to stay away from the various functions, but just look at the IROI developed over time for the various fixes. So that, because if we want to start with the various factors that influence fuel consumption, we can't, that's an endless process. So this is a method that we felt we could use in order, not just to escape, but to, make an accommodation for, how various fixes have been shown to perform over time. I don't know if that answers your question or attempts to answer your question.
Yes, thank you very much.
Thank you.
It looks like we do have a comment here from Tim Anderson. I'm not sure how to respond to it, but we are past the hour now. So thank you for attending today, and thank you, Bernard, for your presentation. If you have any other questions or anything, feel free to reach out to Bernard, and we will see you next month, and watch for that invitation to come later today.